Hey, do you want to learn ROS from 8 top ROS experts from all around the world? Then stay with me. This conference is for you.
Welcome to the ROS Developers Conference. I am very excited. We are going to learn a lot.
Wait a minute, Ricardo. Let me do one thing. Now that's better?
Yeah, that's a lot better, yes!
Hello, welcome!
Welcome to the second ROS Developers Conference.
Yeah, welcome to this second ROS Developer Conference. We are so excited to have you here. And I would like to say good morning to the attendants in America and good afternoon to the attendants in Europe. Also, good evening to the attendants in Asia.
Yes, and this is a very special ROS year.
Exactly. The number of ROS users has increased exponentially.
Yep.
And also in the beginning of this year, we have the new version of ROS 2. And also, there are many big companies are getting into ROS.
Yeah, and that is why we have invited 8 top 10 ROS developers around the world to come here and teach you amazing things about robotics and about ROS especially. The PowerPoint slides, they are getting on fire, guys.
No, Ricardo.
No?
Today, no PowerPoint. No slide, no paper.
Oh.
This is a practice-based conference.
Oh.
The 3 most important things today are practice, and practice. Okay.
And coffee, yeah.
Whatever. So, okay, let's start. Today we will have 4 practical sections, and each one doing 40 minutes plus 10 minutes for Q&A section. Okay, so first we need to see how to open a ROSject. Okay?
Yeah. So remember that we have sent you a link with all the ROSjects that we are going to use during the session today. So you need to open those ROSjects when it's the time, okay? We'll tell you when. So basically how to open a ROSject. A ROSject contains the same content that the author has created, so you can follow and practice at the same time that the speaker is speaking. So how to open this? Let's go to here to the board. So you can see the first thing that you need to have is the link that will get you a copy of the ROSject of the speaker. So click on the link, those links, we have put them on this web page where you are watching the video. So go to that web page, and below there is a link for each one of the speakers. Get the link, click there. This will copy you the ROSject into your zone at the ROS Development Studio. Then the next thing that you need to do is to open the ROSject of the speaker, of the next speaker. So how do you do? Go to the blue button, say More. Click on More. Then next step is to just press Open the ROSject. Then when you open the ROSject, it will start. So maybe it will take a few minutes to open, but once everything is ready, you will be set up to start following the speaker's speech.
Yeah, nice. And remember, in the ROS Development Studio, in the right corner, you have the chat room. So if you have any question, problems during the conference, don't panic. Don't panic. We are here. You can use the chat to contact us to ask any question, okay? And also you can use it to chat with the rest of attendants. Okay?
Yes, exactly. But please, don't put memes up there on the chat, okay? I'm watching, I know you. Let's use it for very serious stuff. Yeah.
Yes, okay. So now let's start with the first presentation. But before that, please open the first project, the one which called Tiago PCL table segmentation. Okay, please get ready with this project. And Ricardo, please tell us what we are going to learn today in this presentation.
So this is the presentation where we are going to learn how to do a table segmentation. So what does it mean? Imagine that you have your robot. You want the robot to bring you the coffee from the kitchen, but then the robot drives the kitchen and doesn't know how to identify the mug that you have on the table. So what we are going to learn here today is how the robot can identify where is the table and which are the objects that are on top of it.
Okay, excellent. So now let me introduce you the first keynote speaker, the CTO at PAL Robotics, Luca Marchionni. Welcome, Luca.
Welcome.
Thank you, Ricardo, for the introduction. I'm Luca from PAL Robotics, and we'll go through an example of how to use PCL libraries from ROS for segmenting objects on top of a table, using a simulation of our Tiago robot, one of the robots that we manufacture in PAL Robotics, and we try to make available to developers for getting started with research from out-of-the-box robot. So the robot comes with already ROS installed, and you will see now how it is simple also with the construct to simulate the robot and use a library for processing point clouds. So the first thing that we have to do in order to start is to launch the gazebo simulation of Tiago robot. And for doing so, we are gonna open a shell that you can do like this. And then we have to run the launch file for Tiago simulation. So this launch file will execute the gazebo simulator and will spawn the robot that is described by URDF, and will already execute all the controllers that are needed for controlling the robot. To visualize the simulator, we have to open the gazebo tool from the tools that we have in the RDS interface, and you will see the robot that is already moving, because the first thing that Tiago does once started is folding its arm and lifting a little bit the torso. So you can see that now that the robot is in front of a table. Yep. What we are gonna do now is that in order to have a better visualization of the objects that are on top of a table, the robot should move the torso and the head. So next step that we are gonna do, we're gonna load some parameter for the motions that allow the robot to move with the controllers that he has already running. So now we are opening a new shell. In this new shell, we are going to execute the following command, the ROS param load. This command will load in the param server of ROS several motions, pre-computed, pre-recorded motions. And for inspecting the motion, we, for instance, can execute ROS param list. And for, let's say, just getting the one that are more interesting for us, than the one for play motion, we are going to use also grep so that it's easier. So all these are the motion that we have just loaded. And now the one that we are interested in is the loop down. Yeah. So now the next command will be to execute this motion, and we can do that by using a graphical user interface that is provided by ROS and that we can execute with this command. So now this will open a graphical user interface to visualize the window. We have to open the graphical tools. You will see the graphical tools opened, and also we can open it in a dedicated tab so that it's better visualized. Okay, so now we have this GUI in which we have to define the name of the motion that we want to execute and other parameters that I will explain now. So for the moment, let's introduce the name of the motion. Look down. We want the robot to move the head down, pointing towards the table, and this is the name of the action to do so. And then we have to replace this parameter that is false with true, because we don't want to use motion planning for this motion. We want to simply execute the motion that is already defined in the YAM file that we previously loaded. So now we send the goal, and you will see that now you should see from your gazebo window that the robot actually lifted the torso a little bit, and now the head is facing towards the table. So with this configuration, the camera can have a better view of the objects on top of the table, and this is what we are going to need, because we are going to use the point cloud captured by the camera in the head of Thiago for segmenting and identifying objects on top of the table. Okay, so now we can close the graphical user interface from the third shell that we open, and we can continue with the information provided by the notebook. Okay, so now we are gonna dig into the table segmentation example, in which we want to process the point cloud and identify what is a table and what is not a table. So for running the example, you should execute this command from this shell. Okay, from the second shell. And now this again will open a graphical user interface. We'll open RVs so that we can now go to the other window in which we have the RVs opened, and you will see now that there are several point clouds presented in this graphical user interface that we can isolate. Okay, now. Okay, so now you can see what is the table. So this is from the original point cloud only what the algorithm that is processing it has identified as a plane, as a table, and then you can also see everything that is considered not tables and that is laying on top of the table. So you would see these small clusters of points that we hope we'll be able to detect as cylindrical objects. Okay, so now we go back to the previous tab of the browser. We can close this node, and what we can do is we can run it again with different parameters without the graphical user interface, because then we'll run the cylinder detector to have a better a further processing of the point cloud and identification of the largest cylinder in front of the table, in front of the robot. Okay, so now let's go through the cylinder detector section of the notebook. We can run the first command in the same shell that we were using now. So we are going to run the Tiago PCL tutorial segment table launch file again, but with a parameter that is not launching RBs. After running this node, we are going to open a new shell. And in the next shell, we are going to run the cylinder detector. Okay, so this is the cylinder detector, and this will also open an RB's graphical user interface, in which we should be able to identify the object on the table. And actually, the algorithm is trying to fit a cylinder object in every cluster of points detected on top of the table. And you could see that not only the point cloud is, let's say, segmented, but also there is a frame attached to the larger cylinder on the scene. And there is also this mesh marker that, let's see if I can. Okay, so this is the let's see if I can. Okay, so this cylinder is actually a cylinder mesh that is projected in the same position of the cluster that is identified as a cylinder in the point cloud, and is centered in the centroid of the cluster. Okay, so now let's put back all the topics. So this is, let's say, the first step that would be needed in order then to grasp this object. Okay, so we need to understand the size of the cylinder, attach a frame to the cylinder to then plan a grasping. Now, if we go back to the notebook, we can go a little bit more in detail into the code that is executing this example. What we have done to speed up the processing and to execute again the example without the need to run the whole simulation that is a little bit too heavy for the computer, what we can do is to use a ROSback. Okay, so now we'll close all the shell. Just 1 second, I can close also this one. Okay, so we will need to, I will also close the gazebo window, we don't need it. Okay, so now we will gonna use a ROSback that is being recorded from the same configuration, so the robot looking at the table, and to do that we are gonna go into, okay, before we have to run a ROS core correctly, because now that there is no simulation, we need the ROS core running in the system. So I'll run the ROS core. So from a second shell, I'm gonna navigate to the folder where the ROSback is stored. You should have access to, so it's in the dataset workspace inside the ROSback folder. And then I will execute this command, so the ROSback play with some parameters to start the ROSback post, and then I also like to use the -k parameter that basically is gonna loop is gonna loop the ROSback, because this ROSback is just lasting 30 seconds, but if we want to use it longer, we can use the -k. So now the ROSback is paused. So to unpause the replay, we need to press the space on the keyboard, but I will wait before doing this so that we can run the same node that we were running before for the cylinder identification, but this time using not the simulation but the topics published with the ROSback. So now again, I'm going to execute the ROS launch Tiago PCL tutorial cylinder detector .launch, and running it will open again RBs in the other window. Okay, now what's happening? Nothing is visible because the ROSback is still paused. So next thing that we have to do is to unpause the ROSback replay. So I go to the shell where I launched the ROSback, I press the space, and now, okay, now what's happening? Now there is this scene represented by the point cloud. We see the cylinder that is detected as the largest one in the scene. We have the projection of the mesh, but now what's happening? That the scene changed. So now I removed from the scene the largest cylinder, and you could see that there is a new cylinder that is being identified as the largest one, the second largest one. So now you could see this, let's say, how the algorithm is continuously processing the point clouds and adapting to a change in the scene with identification of a new cylinder. Okay. What's more, okay, now what we can do, we can go through the code in detail. The most interesting part of this code is for sure the callback of the point cloud. So in this snippet of code, you could see the whole callback that is executed when a point cloud from the RGBD camera of the Tiago head is being received. So the most important part are two calls. One is the cylinder segmentation, and the other one is the statistical outlier removal. So let's now focus on the first function that also I added in this example. And this basically, this cylinder segmentation function is a wrapper of a PCL function call that is called SAC segmentation. So what we want to do is that we want to use RunSAC, that is an iterative method for fitting some model to data. And this data can be noisy, can have outliers. As is the case for the point cloud. You would see you have no perfect cylinder detected. You have shadow in the cloud because of object occlusion. So you have to treat the clusters of points with filters and with some probabilistic methods for allowing you to interpret these points and fit geometrical model, as in this case we have done with cylinder, but also in PCL you can find more objects or more models as cubes, spheres, and different kind of primitive model that you can use for identifying different objects that you can use for grasping or for further algorithm. So in this case, what we do is we prepare this SAC segmentation from normals object of PCL we define several parameters of this object. For instance, the radius of the cylinder that we want to identify, we define a minimum radius and a maximum radius, a maximum number of iterations for the ransack method. Then also we define the model of the cylinder. So we use this SAC model cylinder that is available in PCL, and then also the method used for the fitting. Okay. Once we input the cloud to this method, we can segment it. Okay. And when segment this point cloud, what we will get are these two objects. So the layers, so the points of the original point cloud that best fit the model that we wanted to fit, the cylinder, and then also the parameters of this cylinder. Okay. Once we have this layer, okay, we can then extract the points that are representing the cylinder. Okay, and you can have a look at this basically by looking at the RVs. For instance, let's see if I can remove the previous cloud. Okay. Okay, so I will remove now everything that is not. Okay, so let's also remove the marker, the pose, everything. So the algorithm is identifying this set of points in the whole point cloud as the one that are best representing a cylinder. Why this one and not the others? Because basically there is a filter that also is counting the number of points. So we define a minimum set of points to be considered a cluster, and then every cluster is processed, and this is the largest cluster that is closer to a cylinder in the whole point cloud. A second step that we do after, if you go back to the original callback of the cloud, is a statistical outlier removal, because what could happen is also that you have some isolated points in the cloud that are still considered part of the cluster, but they are not really part of the cylinder. So what you could want to do is to remove also this outlier, and you could do this by simply using a k-mean algorithm in which you define, let's say, a distance threshold on every point. So you basically filter out points that have not sufficient close neighbors, and this will give you this, let's say, clean and isolated cluster of points that then you can fit with a mesh, and you can plot the mesh in the RVs. Okay. So now, additional thing that we can do, we can also see how the segmentation of the region of the point cloud can be tuned by changing some parameter. So for doing this, we are gonna need the simulation running again. I'm gonna go a little bit quick on this to repeat the steps that we have done before. So again, I will start the simulation. So let's go back to the first command that we executed. Let's run the gazebo simulation again. Then we will need again to load a motion. And then also to execute the look down, so that the robot is gonna look at the table from a better okay. We should go back here for setting the look down motion, and again we don't need to plan for the motion, and I click send goal. Goal is active and goal is succeeded. Okay, we don't need the play motion anymore. What we can do also is we can open the gazebo to have a look at the robot, but it's not really nothing new, the same as before, just to be sure that the robot is looking at the table, and you see that the robot is actually pointing the camera towards the objects. Okay, I can also close this one, don't need it. We go to the last section of this document, the notebook, and we can see how to run a new node for isolating different regions. So let's say segmenting cluster and representing them on RBs with different colors. This will open RBs, so let's go. But also will open a dynamic reconfigure window in which we can play with some of the parameters that will change the behaviors of the. Okay, so we have here the, let's maximize the window. Okay, so you could see the Tiago, the cloud that is being colored in different way depending on the region of the segmented cluster. What we can do now is that we have another window here. It's a window that show all the parameters that can be tweaked for changing the behavior of the algorithm. For instance, here we are considering a region as minimum 30 points in the point cloud. If we increase, we will reach the point in which the whole table and floor are considered being the same region. But I mean, just to demonstrate the. Now I go back to the initial configuration in which we had two different colors for the table and the floor. Then what we can also we can increase the minimum cluster size, and this will probably make disappear some of the object on top of the table. Let's see. Or maybe okay, also we can include this one. Okay, this one, this is, yeah, for sure is removing a lot of points too much, but I mean, it's just an example of how to remove a lot of points and speed up a lot the computation, because in this way you have really few points that can describe better a plane. So depending in the application, maybe you are interested just in identifying the table or the floor, so you can play with these parameters to use the PCL filters as better for your application. And more or less that's it. So we can go back to the notebook. I think that we have gone really quick. So if there are any other questions, I am more than happy to answer.
Thank you very much, Luca. So this is Ricardo here, and then for all the people, for all the attendants to that are listening there. So please, if you have any question, write it down on the ROS Developers chat, and we will transfer that to Luca. So Luca will be able to answer that. Then please go to the chat at the ROS Developers chat that you can see on the platform that you are doing the experiments. And in the meantime, that you are preparing your questions, let me start myself with the first question. Okay, so Luca, here is my question for you. And then you have shown us how to detect objects like cylinders or boxes or spheres by using the PCL library with basic shapes. But how would you think that we can apply the same system to detect objects with other shapes that are the composition of those shapes? Yeah. Is that possible to do it with the PCL directly, or we have to develop something?
I mean, is it possible, but you have to develop something. So there are several ways. One is by knowing the object, you can create a model of the object using a point cloud. So let's say you can have a point cloud describing the ideal object that you want to recognize. Mm-hmm. And then by processing the current PCL point cloud, you can match what you are seeing with the model. So you can do something like ICP, that is another of the function available in PCL library. So it's an iterative closest point that is trying to minimize the distance of every point from the current data to the previously recorded point cloud. Mm-hmm. So this is one method. It's a little bit brute force, but it's something that, I mean, can be used. Especially this is used for 3D mapping, 3D SLAM. So to align different point clouds, this is one of the methods that is used. Alternatively, what can be done is to create, if you have the CAD model of the object, mm-hmm. you can do something similar to what we have done with the simple cylinder. So you have let's say a mesh that describes the object, some geometrical surfaces, and again, from the point cloud, you can extract surfaces, you can extract normals to the surfaces, and then you can use this data, this information, for fitting it with the model that you have available.
Okay, yeah, I see. So you have to build your own model, and for the
or you can download it.
Or download it already. Yeah, that's right. Good
yeah, there are a lot of examples of, let's say, libraries that try to use information available on the web to download IKEA furniture models to then use this knowledge as a model for understanding the data that the robot is seeing.
Okay, great. I have here a few questions more for you. I don't know about that one, but let me ask you about that. That is a question by Ludovic, who is on the chat, and then he says, what scientific papers and methods are used for the methods that are used there? So can you provide any reference? So
from what I know, I've been using Ransack, that is a famous method used for almost everything that has to do with data fitting or outliers filtering. Mm-hmm. And I think this is something that was developed in SRI in the 80s, I think, and was mostly used in image processing at the beginning. Now is common for PCL, for point clouds, or for 3D data. And there should be some publication on the 80s. It's really something, let's say, consolidated now. That is part of many more algorithm and publication that have to do with that data treatment, the real data treatment. Then for the other, I mean, also object segmentation and plain or let's say clustering data. There is a lot of literature about this, especially for then semantic interpretation of the data. I cannot now specify real papers, but I think that this is something quite easy to retrieve.
On Google, yeah.
I mean, maybe, I mean, if we can, I mean, if the person that made the question is interested, can contact me. I can point in to more precise references.
Great, thank you, Luca. So you know Lubomir, you can contact him directly. Then we have here some more questions, and since we are good on time, let me go with them. Then Diomedes School, that's the nickname of the guy, or no. Then he says, could you give a quick explanation on how to do grasping on that object? What is required?
Yeah. Okay, so there is, let's say, an easy way and a more complicated way.
Yeah.
So let's say the one possible approach could be, once you know the position of the object and you know the, let's say, the diameter of the cylinder that you have recognized, you can define a point where the gripper can approach the object to then execute the grasping. Yeah?
Yeah.
So let's say for the cylinder we can specify a point, I don't know, with a little bit far from the center of the cylinder, from the surface. So let's say we can plan a trajectory of the arm and the gripper collision free to approach the object, and once we reach that position, we can simply command the gripper to close to try to grasp the object. So this is one option. That is, let's say, the most common used in our case for Thiago, we do this for grasping, especially, let's say, easy object like cylinder and boxes or spheres that are, let's say, easy to identify and easy to recognize on top of a table. The other more complicated method could be once you want to also plan the grasping points on the object. So that could be the case for more complicated objects, or for objects that should be grasped, for instance, a cup. If you have a cup, you want to grasp maybe from here only.
Yeah.
And maybe you also need to have in contact with the object just special point of your gripper, not the whole gripper. Yeah. So in that case, I mean, it's like as complicated as motion planning. So you have the surface of the object, you can plan grasping point on the surface, and then for every possible grasping point, you can try to get a configuration of your robot that is feasible. Yeah.
Okay.
So in that case, it's the same. Once you have a solution of the inverse kinematics that place the gripper and the arm of your robot in the position that you need for the grasping, you can plan a motion of the whole arm and gripper to reach the pre-grasping position, and then approach the object and grasp it.
Yeah. Okay.
So and this can be done, for instance, in ROS using Move It application.
Okay. Yeah.
Is a way.
Yes, that's a very convenient way because it's already integrated in ROS and it provides quite good results. Okay, so a couple of questions more. So, Benu Samprati, he says, can this method be used for obstacle detection? If yes, what is the typical response time of the system to identify the object?
the answer is yes. The response time is not as quick as we could need for navigation. So in our case, I think that the streaming of the point cloud is at 30 Hz, but we need almost 1 second for processing it. Yeah. So the system is not real time.
Yeah.
In the sense that you cannot process all the point clouds that the sensor is generating. Yeah.
Mm-hmm.
And what you can do is you can downsample. Yeah. So depending on the size of the object, you can reduce the resolution of the point cloud to speed up the processing, and that can help in at least being, I don't know, maybe reaching 10 Hz. That is something that more or less is already enough for obstacle avoidance of mobile robots.
Yes.
That can avoid obstacles on the ground, detect, like to say, free ways for crossing doors, or normal situation.
Yes, and that's the next question is quite related to this one. They mentioned about downsizing. It's a question from Erlin. He says, how many points are there in the point cloud? And are there any problems with the network infrastructure due to data transfer?
Yeah, the processing that with the simulation, you have the same resolution of the sensor. In our case, on Tiago, we have an Orbe Castra RGBD camera,
mm-hmm.
and which has a point cloud that is, I think, is 640 by, let's see, again, it's 640 by 480 points. So we are.
Google is our friend.
So it's like 300,000 points. Yeah. Okay. So it's quite enough. Every point cloud has 300,000 points, and also, and this is one. In the case of there are cameras that are even more detailed. Or imagine if you are using Velodyne or any 3D laser, you can have 1,000,000 points per point cloud. So it's complicated. What we do in the robot is to process the point cloud directly on the robot, and in case you need real time or almost real time point cloud processing, we have an architecture of control that has a dedicated computer just for the image processing or point cloud processing of the robot. Mm-hmm. Yeah. Also, we have a configuration of Tiago that is using in NVIDIA Jetson. Mm-hmm. So the camera can be connected to the NVIDIA Jetson, and in the case you can benefit from the parallel computing and the powerful GPU of the NVIDIA Jetson for speeding up the point cloud processing. But it's true that the data streaming at 30 frames per second of a point cloud can collapse the Wi-Fi or make some delay, introduce some delay in the communication with robot if you are gonna process the point cloud off board, yeah, not on the robot. So what we are, to solve this problem again, or you reduce the bandwidth, so you, instead of streaming out the point cloud at 30 frames per second, you can decide, okay, let's stream it to 2-3 frames per second. So in that case, you can reduce the latency and the load of the Wi-Fi connection to the robot, or you can again downsample the point cloud to make it lightweight. And I know that there are some libraries, especially designed for point cloud and high data, let's say heavy data streaming over ROS. I don't remember now the name, but basically, because the problem with point cloud is that when you send them as a ROS topic, there is a deep copy of the data. Mm. So there is an inefficiency introduced by the way how ROS topics are treated. And I think that the guy from Tango project in the US,
Yeah.
they developed a way that is called like direct copy or something that optimize this data transfer and allow to have almost real-time point cloud streaming over Wi-Fi.
Okay, yes, I remember also doing some other tricks, like for example, not getting the data from the point cloud until you really need it. So there is no publication of the point cloud until somebody is requesting a single scan, and then that scan is done, and then got the data, and then stop. So by doing this, is you can reduce a lot of computation. Okay, so the people here say thank you for answering that. And then a final question for you, Luca. That is from Lubomir again. The second question, he says, is there a database or data set of objects, models that you usually use for object identification, for a spoon, for a map, for something? Any data set that's available?
I don't know exactly now the references, but there are many database of CAD models of common objects that can be retrieved from the internet. Or actually there are projects in which everything is, let's say, in the cloud. So you just you can access this as a service.
And then you send the point cloud to that computer cloud, and then they will.
Exactly.
Okay. Okay, so I think it's everything for Luca's presentation. So let's thank the speaker again.
Thank you very much, Ricardo, and everybody. It's really a nice conference. I hope that you can enjoy today and tomorrow with the rest of the speakers.
Thank you very much. Yes, so here we are, and
thank you, Luca. No, very good presentation, and thank you for your answers. I think it was very inspiring for us on how to use it on our own recognition projects, right?
Yes, that's right. But I tried to make it recognized with some time, and it didn't work. So I don't know. Maybe I will have to ask Luca later.
Whatever. Okay, so let's move on. Please remember now, get ready with the second ROSject, the one called porting a node from ROS 1 to ROS 2. Please open it, click more, click open ROSject, and get ready with this ROSject in your screen, okay? Yeah. So before that, let's have some fun.
Yeah.
Please tell us, where's the fun?
Oh, the fun is that we have a surprise for you. In the meantime that we are preparing the next speaker, so we don't want you to be there just waiting there. So we got a lottery for you. Actually, it's a lottery. I mean, we are going to provide you, we are going to do a lottery for a winner who is going to win this ROS Developers t-shirt that we have prepared for you. Okay, so how can you win this t-shirt? I am a ROS developer. How can you win it? Very simple. We are going to put a question here on the screen that is related about what the previous speaker has said. It's a very easy question, okay? So the first one that provides a right answer on the chat, the right answer on the chat, the first one, he will win this t-shirt. Okay, so we are about to project the question here. And here we have, what does PCL stand for? Exactly, Dan Martinez. So you will receive shortly the t-shirt.
Well done.
And now it's time that we switch to the next speaker, who is already prepared and ready, eager to teach you about a very, very interesting subject. So you know that ROS 2 is the future of ROS, yeah? And the problem is that we still have a lot of code that is running in ROS 1. So we have to start thinking about how to transition our code from ROS 1 to ROS 2. That's specifically the subject of the next speaker, how to transition a node in ROS1 into a node of ROS2.
Yeah, so let's welcome the second keynote speaker, the software engineer in Fraunhofer IPA, Ludovic Delval. Welcome, Ludovic.
Yes.
So, hello everyone. So I'm Ludovic from Ludovic Delval from the Institute Fraunhofer in Stuttgart. So thanks to the Construct to organizing the conference and invited us to do a talk. For those who don't know Fraunhofer IPA and our relation with ROS Industrial. So Fraunhofer IPA is one of the biggest research institute in Germany, one of the biggest Fraunhofer Institute, and we are field of application within the industry and the robotic and automation. And since now 6 years, we are the coordinator of the ROS Industrial Consortium Europe, and also contributor to ROS Industrial. So for those who don't know really what ROS Industrial is, ROS Industrial is not a fork. It's a common mistake that some people think. Is not a fork of ROS with industrial purpose. It's more like ROS agriculture or ROS humanoid. It's like we create some package, or we fork some package and use them in a different way. But this is basically it. It's a subset of ROS packages that has for goal to be for industrial purpose. Since now 2 years, I'm a teacher. I'm teaching ROS to the industrial who request it within the European project ROSIN, which can, if you're an industrial, there is some funding opportunities if you want to have a look for developing some ROS packages. Here's a link, so please check. So today I'm gonna talk about how to switch from ROS1 to ROS2. I will focus on Python for the purpose of simplicity and not having to talk too much time about the compiler and thing. So why I chose this subject is because I think now it's a good time, if you have already some ROS1 packages, that it's a good time to switch to ROS2 because the first LTS of ROS2, which is very stable, has been released 2 weeks ago. It's ROS2 Dashing. It contains everything that you need, and then there's going to be just one last ROS1 LTS support, which is going to last for 5 years. But still, if you want to contribute, I think it's a good start to start now, because the basic API, everything is not going to change that much, so you can start to think about going to ROS2. So I will cover how to switch from ROS1 to ROS2 with simple packages. Then I will explain also that it's possible to communicate between ROS1 and ROS2, so you don't have to port everything to ROS2 at one time. You can pass smaller part and then continue working with ROS1. The biggest part that are core to you and needs more refined work, you can keep them in ROS1. And also how the build system in ROS2 is different from ROS1, especially for Python package. So that's my goal today, is to introduce you to new ROS2 concepts and see how we can move from ROS1 to ROS2. So let's start now. Yeah. So if you go on here, you will see that if you open the IDE, there is a ROSDev workspace, which was my ROS1 workspace. I tried to make it a typical workspace with small packages. So there is 4 packages: one talker, one listener. One is with my custom message that is exchanged between the listener and talker, and one bring up just to have my launch file and everything. So yeah, we can have a look at the script, but I try to follow the best practices as much as I can. So the listener, even if it's a Python script, as is an executable, doesn't have the Py extension. There is in my CMake list how to install the Python package here. The same, the dependencies are sorted out to be just dependent on my custom message. My custom message is very simple, it's just a string and a unit. It was just for purpose of the example, but the complex here is not. And then there is a talker, which is a typical publisher based on a rate, and I want to insist that this one is based on a rate, so it means that it's trying at best to do at 10 Hz frequency. And this is a bit different that because in ROS2 you cannot use this rate API anymore. So that's the typical workspace, so we can try to compile it. So I suggest first to always try from contain make, of course. So yeah, so I already built it just before. Then we need to source, and we can try the bring up, for example. Yep. French keyboard. Last one, bring up. So yeah, here, so it's going to start the master, everything, nothing new here. And yeah, it's the talker and the publish and the subscriber on the same terminal, but this is two different nodes and two different processes that are called here, because in ROS1 you cannot have both in the same process. If we have time at the end, I will try to go to this point saying, okay, you can now in ROS2 doing multiple things in different way, and you have nodlets in ROS2 for Python, because everything is a nodlet basically. But yeah, that just to show a bit the ROS1 workspace, typical workspace. Now let's start to go to ROS2. So let's start. So here, if we check the dependency, we have to do it in a proper order, because here I depend on my custom message, here I depend on my custom message, and my bring up also depend on the listener and the talker. So I first need to port my ROS1 custom message, then the listener and the talker, and then the bring up. So, oh yeah, one thing that I want also to highlight is that you need everything to work from the install workspace. So in case you don't know what the install workspace is and how it's different from the Delval workspace, the install workspace is basically a standalone workspace. So it's not linked to your source, it's everything inside it. And it's important that you have everything installed in the CMake and things, otherwise it won't work from the install workspace. And in ROS2, there is no more Delval workspace, so it means that you have to install everything. So be careful before porting to ROS1 to ROS2. Try to compile your install workspace and try your node before, just to be sure that everything is working. So let's start a ROS core. Well, yeah, so here, and yeah, so it's working, of course, but yeah, just to tell you that you have to be sure that it's working from the install workspace. Here, actually, here I forget to source from the install workspace. Yeah, but yeah, so don't forget to source also from the install workspace. But yeah, that's an important thing before switching from ROS1 to ROS2. Be sure that everything is working from your install workspace. Then now let's go to. I'm gonna get a new terminal. Yeah. So let's start going to ROS2. So let's first create nice ROS2 dev. ROS to dev workspace. I will try to stick to what I wrote. Source, and I'm here. Now that what I've did here is to create a ROS to dev workspace. So in case you are lost at some point, so I have backups the final look of the ROS to dev workspace, so you can have a look of the script or thing like this in case you're lost at some point. But yeah, so let's go into the here, and I want to copy. So a good way is basically to copy paste your ROS1. So I say custom message first, and then copy here in the source. Oops, minus error. And I want also to copy the listener. So I will start for the listener first, just to highlight the use of the bridge between ROS1 and ROS2. Okay, so now that we have this, let's refresh, and we have a nice ROS2 dev workspace with custom ROS1 package that are here. And now let's start to talk about ROS2. So in ROS2 there is 2 steps that you need to do, is change the API and change the build system, because we in ROS2 it's no more Catkin, it's Colcon, and the build tool is Ament. So Colcon is the build system and build tool is Ament. So there has been a few changes here and there in the API, so I will describe them, but basically here we are switched from CMake version, and you don't have the Catkin anymore, it's now Ament, and you have to say that it's an Ament package. So I'm going to copy paste because I cannot type this without doing any mistakes. But yeah, so here I have my ROS2 custom messages. I explain some compilation arguments that I can pass, and then I need to find CMake, the built-in interface, because here I'm building a message, so I need to call the built-in interface, which is going to call the DDS wrapper. So now in ROS2 there is the communication layer is a DDS, and the most common one, at least that I use, is fast HTTPS, which is a DDS implementation. And here this built-in interface is actually the interface between ROS and the communication layer. So here we need to generate this, and this is meant to be agnostic. So if you change then your DDS implementation for something else, you don't have to change anything in your CMake list. And this is a big thing in ROS2. It's totally agnostic from the communication layer, and this is very nice, especially for industrial application, because some people want to use fast HTTPS, but there is also other things. And the package XML is also needs to be changed. So there is, it's not much to change. It's the format is the same, but it's format 3 now, so the new thing. And of course you have the difference between, as I say, you need the build interface, you need the ROS ideal default generator. You need to say that it's an interface package in order for the message to be found as a potential interface definition. And you need to export the CMake. So here, and this is pretty much all you need to do. So for sake the consistency reason, I will rename it ROS2. Let's not duplicate our work here. Let's refresh. But yeah, that's basically it. So you need to change the CMake for porting a message, change the CMake, change the package XML. don't forget to implement also license if you release code afterwards. It's always nice to have a license to know that other people can use your code. It's not only for you, but also for other people. And yeah, so that's for the custom messages. Now in the listener. So in the listener, it's a bit different because first thing, we don't need the CMake list anymore, because now in the ROS queue, we're not gonna call CMake for something that is Python, and that's also a good point for ROS queue, because calling CMake just to call then Python to make things doesn't make sense. So the calling directly Python as it's a pure Python package. So let's remove the CMake text. Before I do anything else, let's rename it ROS2 listener. Here, now, in the best practices in ROS2, it's always nice to have a library within your package, Python library. So I'm going to create it right now, which I'm going to call ROS2 listener. Here, and then I just put my script inside. In order for Python to find it, I need to make an init.py within. Nothing in the init.py. Here I can also put another init.py for my module to be found here. And this is pretty much looks like a real Python package. It's no more some kind of ROSPy, or it's a Python package, because this is the goal here, is to say, okay, I don't have anymore a ROSPy package which I cannot use in Python, or I need to do some tweaks. No, it's a Python package that's going to use ROS, and that's a good thing. And also here, because now you have a new thing in the setup.py that we're gonna talk just after, I can also keep the extension here, because here it will not matter if it's a Python or things. There is an abstraction in the setup.py to say that's an executable and I want to call it that way. And that's also a nice thing, that we can keep the extension. Now, let's talk about the package XML. So, of course, we need to change the name to ROS2. Let's try to keep some consistency here and say it's now a ROS2 subscriber. And of course, I don't depend anymore on the custom message. I depend on the ROS2 custom message. Now, it's not ROSPy anymore, it's RCL, so ROS Core Library, which is a C version. That's the core of ROS, and the Pi extension is just to say that we're going to use the Pi client implementation here. And of course, it's an exec depend because Python doesn't build, so we don't call anything here, but we still need to call the builder, but we don't call amen CMake here, we call the amen Python because it's a Python package. Build type, yeah, and then we just get rid of this by calling that it's yeah, we don't need this anymore. We just need to call the and that's it. And now let's try, and if I didn't do any mistake, it should work. But we didn't port yet the listener.py. No, it won't work because I forget one big step. It's the setup.py, which coming next. And the setup.py is actually now a real setup.py. This setup.py is what is called by Python when created the Python package and not a ROS package. And this you need to describe your package, basically what you have done in the package.xml, which is for ROS, but now you need to do it for Python. And I'm gonna copy paste because otherwise it's a bit too complicated for me to write this without any mistakes. Oops, I keep a line here, which it shouldn't be. Yeah, don't forget to save. And yeah, so I'm going to explain a bit what's going on here. So package name is the ROS2 listener. This is meant for avoiding code duplication. And yeah, just to say, okay, I'm using the package name in two different places. I want to make them avoid code duplication here. Then I just say that I need the setup tool as a install. Find packages is if I need some specific packages for Python. Package name is the data file is a way to register your package.xml within the Python system. And yeah, so it describes the author. Author is Rajesh, is one of my colleagues. The maintainer, so of course fill that. Then the intended audience, so everything that you put in the Python description, that means, and yeah. And you also need to do a few things, but we come to that later. On top of that, we need to create a setup config file to know. So before I said that we need to install everything, so now we need to know where to install everything. And this setup config tells where you want to install things. So it's a very simple file that we setup.ffg. And here we're gonna do that. And here is it. Here I say, okay, oops, I forget. So here I say that I want to install my, for development, I want to install my script here, or because I want to also keep the consistency between my development and when I have installation, I say the same thing. But yeah, this is to say, okay, you can find my folders here and my script here when I will install everything or when I will compile with Qualcomm. Now let's go to the API, the Python API. So ROSPy is not something anymore. Now it's RCLPy. So that's the typical ROS2 API. And on top of that, I want to import, for clarity reasons, I want to import the node, because now node is a class that so everything's going to be a node, or as I say, it's now a nodelet. So here I say standard messages, but we can keep. But for using the bridge later, I will show with standard messages. So here I will gonna keep the display thing, and now just pretty much okay. So now I just fixed my import. Now let's talk about the main class. So before we had in ROS1 we had initialized a Python node, and then we had a class that we called that was gonna run some callback, some subscriber, some publisher, and the spin, and we spin about the node. In ROS2 it's better to make your class a node, and we will see that if we have time later, but yeah, it's better to make it a node in order, because now RCLPi doesn't do really the spin, so you can do the same, of course, and that was how I started first. But now it's better to put in a node for be able to put multiple nodes within a simple Python file, and for some case that you can have, it can make sense. So, but we could have stayed the same, but I will stick to the best practices that say it's better to make a node for reusability. And as it's a node, I need to initialize my node class. So here I'm calling the super, which gonna call the node. And one of the arguments for initialize the node, as before, is the name of the node. So here I say init node and I give a name. Here I say init node, which super called node, and the ROS2 listener. And the subscriber is a bit also, we don't have a class called subscriber. We say that we create a subscription within the node. So as it's a node, if it wasn't a node, I had to pass the node as a parameter and then create the subscription. So it would have been a bit different, but yeah, it's doable. You can keep the same way, but I want to also show you a bit new way of doing things with ROS2. The order has changed a bit, so yeah, it's now the message type, then the topic name, and then the callback that you're gonna call. The callback function is the same, but it's not ROSPy log info anymore. It's actually now it's get logger, because the logger is something else also that is related to the node. So it's self get logger, which is a function of the node. So also a good reason to make your class a node. And now I just want to do a ROS2 listener. I have received blah blah blah. And now my main. So my main is always I separate the main from the main. Doesn't make really much sense here, but still the best practice is to do that. If I want to call main from something else at some point, I don't know. And also here, as I said, we don't initialize a node, we initialize an executor, but yeah, we don't really have to do that now because we just have one node, so we don't have to care too much about the executor. It's just going to be simple. And now I want to say, okay, I create an instance of node here, which is going to be a ROS2 listener, and then I'm gonna, as I said, there is this executor thing, which I'm gonna explain later a bit more what is this about. But in this executor, I can tell which node I want to run. And here I want to spend a node. But as I have an executor, I need to, so here with the spin function, it's gonna shut down on its own when I kill this, but then yeah, I need to kill my node and shut down the call here. And this is it for porting from ROS1 to ROS2 for the subscriber. It's not that hard and doesn't change that much. You still keep the same spirit here and there. You don't have to worry too much about new API except for the time API that we come later with the talker. But that's basically it, and you have done pretty much here. But yeah, I want to also add something here. Is this entry point, and this entry point is basically why you don't need the dot. You can keep the .py is because you can say, okay, I want to access my script, which is in the ROS2 listener scripts. Yeah, I did it right, listener, and I want to call the main function and the listener, and I want to call it listener, and this will actually call the listener.py, but it will make it py agnostic. So everything here is nice, and you don't have to find too much. And everything in the Python package make it seamless between ROS2 and ROS and Python. So it's really nice. So now let's try here, and I want to get to source opt ROS crystal. Yep, setup.bash. So you will see that there is local setup.bash and setup.bash. The difference between the two is local setup.bash is on its own, and setup.bash is linked with other work package, with other workspace. That's the difference. And now we're gonna code build, and it's gonna build here. Seems that I did the same. Okay, sorry about that. So yeah, let's keep it, because yeah, typing can be troublesome sometimes. But yeah, let's go in the so and current build. So it seems that I may have done a mistake in typing somewhere, but yeah, sorry about that. Yeah. So it's gonna take a bit while to finish to install everything here. It's because it's creating new files and new things every time. So when you call from ContCon, it's gonna take some time. But yeah, so now I want to source, but here I will source the local setup.bash, because I don't want to load everything when having this. Oh. Sorry about that. He said that he's not found. Yeah, I tried everything just before, of course. Yeah, no. Yeah, that's no. Why? Okay, of course. I wanted to avoid doing that, but it seems that I have to. So yeah, here you have this safe flags that are appearing sometimes. So it's a thing that you can put in the setup.py. That's just saying, okay, I can actually run my script from a zip file. That's you can say zip safe equal true, and it will gonna run from the zip file. So sorry about that. So okay, so now let's hope everything has been. Why you cannot find the ROS2 custom message? Okay, anyway, that should still work, right? ROS2. No. Fuck. I cannot find this. I'm really sorry about this. I'm gonna move the ROS to custom message to some other place.
Okay. So here, this is Ricardo. Don't worry, you
Yeah.
are great there. So it's normal to have some mistakes. Then take your time for solving it. So
Okay.
no,
Okay. Yeah. Sorry about that. So I tried this just before, and everything was working, and seems that I have changed the things between. So let me just find, take my restart setup.bash, just to be sure that I'm restarting with something fresh. I'm gonna try. Yeah. So here I am in the ROSDS. Yeah. Okay, sorry about that. I'm gonna have a look. So here, what did I do? It's exactly the same. Yeah, there is the error. Yeah, that's a problem of ROS 2 right now, is when you do an error somewhere, it's not that easy to find it. So that's a bit an issue right now. Yeah, sorry. Everything, yeah, that's because, yeah, right now everything is running in different ways, so yeah, sorry about that. So anyway, let's continue now, and very sorry about that. ROS2 debug system and how to find this error in there are not very clear, and it's going to be improved, and in dashing is already quite improved, but yeah, here. So now I can install my setup.bash. Oh yeah, I need to let's start from a fresh terminal, because here I can yeah, source install setup.bash here, and I can ROS to run my listener, so it's in the ROS to listener. Oops, yeah, I say local setup.bash. Sorry, I'm a bit panicking now, but no worries. So ROS to run and I forget to source ROS to crystal setup.bash. So here now I'm sourcing this. So here it's a good way of sourcing your workspace, sourcing the crystal or dashing, and then source the local setup.bash. And now you can do ROS to run, ROS to listener, and the listener. Yeah, and yeah, here it's not doing anything, but if we go here, it starts a ROS core, and I can actually or I can do it from here. Here I can source my ROS1 my ROS dev workspace, install setup.bash, and I say we can do ROS1 ROS1 Docker and Docker. here. So here it's publishing. So now I need a bridge between ROS1 and ROS2. And how to do that is actually, okay, I'm gonna do it from here. You have in ROS2 a nice tool which is the ROS bridge, but to run it you need to source first ROS1, so opt ROS melodic setup.bash, and the crystal setup.bash. And now that you have both sourced, you can to run ROS1 bridge and dynamic bridge. And here, yeah, we can see, okay, yeah, that's what I said. That's because you need the custom message. And to compile this, I explain you here. I won't go through it, but I explain you how to run the custom, how to build the custom message. It's going to take a long time, and we are already quite short. So I'm not going to express it, but here you can see that, yeah, it's try to connect the two, but it doesn't know the message display. So it needs to do that. That's why if you want to try it, you can do it with a string message, simple string message. Now I will go through the talker, and I will not type anything just to save some time. But yeah, so if you go in the here in the talker.py, if you go in the package XML, the setup.py and the setup config, it's going to be similar to what I explained about the listener, so I don't want to go through again. But in the talker, the difference, I said, it's this rate thing. It's is with this rate publisher. So if we open the talker again, just to highlight it, where is my ROS? There, yeah, here. Talker. So here I have something that need a rate, and you need to sleep to have the frequency. But this you cannot do anymore in ROS2 because there is no time API yet. So one thing that you can do, and the solution that works, is to create a timer, a simple timer with a callback, and say, okay, I'm gonna publish at this rate, and I'm gonna on the callback of the timer, I'm publishing, and it's the same. So I'm just filling the message counter, message get logger here, and then I'm gonna spin the node, destroy the node, and shut down the node. I'm gonna go through the launch file because it's a different thing. So now it's a Python file. So right now there is no XML file for the Python, the ROS2 bring up. So I explained a bit here how the bring up is gonna go. But yeah, so the bring up is now a launch file, and you can do a lot of things within the launch description. You can start a node. You can wait for another node to be started in order to be able to start. So there is this lifecycle management here that you can express within the launch description. It's kind of nice. And the last thing that I wanted to talk, and I'm sorry I explained a bit too much my time here, but yeah, is this mixed nodes. So here I created a simple ROS2 package with the listener and the talker within the same package. And as I said, there is this executor, which is the RCLPy, and actually in the executor you can pass nodes inside them, and you can have the talker, the listener, and you can say add node talker listener. You can then spin. So spin, it means that it's going to spin both node within a single thread. There is also multiple thread. You have async, so there is multiple way of doing that. And this is just a way to tell you that you can actually now do nodelets within Python. And if you're doing some Python development, as I am, it's kind of interesting to be able to run multiple nodes within the same process. I can show you a bit how it's gonna work. So let me go slower. Okay, and now I'm going to do ROS2 run, ROS2 Docker mixed, and the Docker mixed. And now you have in one process, so it's a ROS run, it's not a ROS launch, both publisher and subscriber. And one thing it's important to highlight here is that they're not using DDS here, they are using memory sharing, and it's much more faster. And yeah, that's it. So that's everything that I wanted to talk here. Sorry I expand a bit the time, but thank you for hearing, and sorry for the problem. So I hope you learn something, and yeah, pay attention when you're writing this package XML and this CMX, because yeah, the errors are quite hard to find. Thank you.
Okay, thanks a lot, Louis. Thanks a lot. So can you share your webcam?
Yeah. Yeah. So yeah, live programming is a thing, and yeah, that's why it's hard to do. And yeah, sorry, yeah, this error, I try to pay attention, and yeah.
I think he deserves another round of applause.
Thank you.
Okay, so
And now it's time for the questions. So people on the chat, please, if you have any question, start writing your questions on the chat for Ludovic. And just before the people start to put the question, because there's a small delay between what we are talking here right now with you, Ludovic, and the people receiving, then let me ask you the first question myself. So
yes.
The first question is that you have shown how to translate, let's say, from ROS1 to ROS2 Python node, and it entails a lot of work. And so, are you aware if there is any automatic tool that can help us to translate in a big bunch of code from ROS1 to ROS2?
Right now, I don't think there is any. So this is yeah, that's a thing that is a lot of discussion, because yeah, more than the API translation. So there is this API translation, but I don't think it will be available soonish, because I guess ROS2 is, of course, for simple node like this, it doesn't show all the potential, but you can really think new way of doing ROS2 nodes and nodelets, and this is hard to translate one-to-one API, because yeah, one-to-one API is probably something that is not the best way to start from ROS2. Is a way to translate, and then you build up on that for simple things. It can be pretty much applicable. I would say that this tool can be applicable, but for much bigger and much more complex application, you will need to think a bit more. For example, this time API that doesn't exist, or if you want to combine some nodes within the same process. All of this you can do in ROS2, and it's probably the best way of doing this in ROS2. Translating one-to-one is a way of starting, and probably some tools will be created to do that, but the best way may be to think differently.
Okay, then we have quite a lot of questions. Let's select some of them, because a lot of people of questions here. And then let's go with the first one from Danny Das, that he says, Ludovic, do you know if using the bridge affects significantly the performance? And he means if you're publishing, for example, a point cloud data, does the bridge have to parse the whole message or just route it?
No, actually, it's gonna pass the message, and yeah, for this you use actually it's better to compile the node yourself and maybe trick the bridge yourself for big messages, because yeah, the bridge is actually a ROS1 and a ROS2 nodes at the same time, and is actually yeah parsing from ROS2 as a subscriber, reading it, and make the templates for ROS1 and sending it. So it's gonna take a lot of time, even if ROS2 is much more efficient. But yeah, it's probably you can tweak the bridge in order to fine tune for this application, I guess. We did that for the action, but yeah, it's better to not pass too much big message here for through the bridge, even if it's efficient. But yeah.
Yeah. Okay, so here another question more about your opinion as an expert in the field. It's a question from Biomed School, and he says, do you recommend to still, based on your experience in the field and the market, do you recommend to still working on ROS1 or moving forward to ROS2 directly?
So I would say now, if you want to start, if you have a fresh start, I would say start from ROS2, and if there is a package that doesn't exist for you in ROS1, just use the bridge right now. But most of the packages are in the process of being ported, move base, and a lot of what I call core package are being moved to ROS2. So right now, I think if you don't have and if you want to start fresh, start from ROS2. But if you have already some dependencies and you know that they're going to take some time to be ported to ROS2, so I would say stick to ROS1 is actually the most used one, and probably still the best right now, even if ROS2 has so much new things and it's so fresh to discover any new features. I still do most of my work on ROS1.
Okay, then this another question from Raul Pando, that he says, how much the conversion process will be affected by using C++ instead of Python? Because
yeah, I did that for C++. It's pretty much the same, so you need to change the APIs and the way the node is so you don't have to pass the node handler anymore, because now your class is a node. But I wanted to cover Python because C++ translation is actually quite well covered on the ROS2 in one of the ROS2 tutorials, and not that much for Python. So that's for C++ is pretty much the same as this. You don't have that much overhead, except for the compile part that you need to call amend and amend CMake and do all the CMake file that I did in the setup.py. Here you have to fill the CMake file.
Okay, so we have many more questions there, but the time is up now. So we have just to thank you very much again, Ludovic.
Thank you for inviting me, or inviting us, I would say, as ROS Industrial. And best wish for the rest of the conference. So I saw the first presentation, quite interesting. So, and if you have more questions, so Ricardo, you have my email, so feel free to give for people that are interested.
Ludovic was explaining about the DDS communication protocol that is inside ROS2. He said that is implementation agnostic. And then I don't know that if that would imply that ROS2 doesn't believe in God, or...
What?
Yeah.
Whatever, stop it.
Okay. Okay. So maybe I will ask him later. Yeah.
Let's have some fun, okay?
Yes.
During next lottery, and please answer we will show you a question related to the previous presentation. And as the last lottery, the first one who answer the question in the chat room will get a t-shirt of I am ROS Developer, okay?
Let's go. So the question is, what is the name of the latest release of ROS2?
cover a very basic, but I think really important topic, ROSject, basically, that we are going to essentially build PanAndTilt simulation, and then we're going to use that simulation to generate some code so that we can do phase tracking in simulation. And once we have it, then we will use all that knowledge to apply it in a real robot, which we will connect through ROS Development Studio. And we'll test that our code works. So essentially, I've left in the notebook information about the web, and also if you have any questions whatsoever, just email me at on my account, and I'll answer all your questions gladly. Okay. So the motivation of this speech is basically to learn basic ROS, how to go from this real robot that we have, a PanAndTilt in this case with a Raspberry Pi. So how to go from a simulation to this real one. Yeah, and then we will cover a bit how to connect easily to this robot. Yeah, I'll go explaining the code. I won't generate all the code because it's a lot of code to generate in 40 minutes, but I'll try to explain all the main details and the things that I found difficult and challenging, and I think that you'll find problems. Okay, so let's start. So if you go to this first notebook, simulation of the PanAndTilt, so I always recommend, and this is something that not a lot of people in the robotics business do, sadly, is that when you want to work with real robots, you can't start with the real robot. You have to start with the simulation. This has mainly one advantage, which is energy consumption. So if you generate a simulation of your real robot, you'll spend more time coding and less time spent in hardware issues and connection issues, and basically you'll go much faster developing the code. So here in the construct, we always recommend to generate and work with a simulation 90% of your code, and then the other 10% work on the real, and you have to adapt. Always you'll have to adapt something that you didn't have in mind when you were coding for the simulation. Yeah, or maybe the simulation wasn't well done. Yeah. So let's start the simulation, shall we? So the first thing is we're going to start a simulation. There are various ways to do it in ROS Development Studio, but the basic one would be to just go to simulations from my workspace, and then look into all the list of launches that it's automatically detected by ROS Development Studio, but in your local computer would be exactly the same, just that you would launch it through the web shell. Yeah. So we go here and we select PanAndTilt description, main simulation, and we hit launch. While we wait that this launches, you can open here in Tools, the IDE, and then you can open here in another tab. I already done that, so let's have a look. So while it loads, we're going to go through the code. So essentially, in this ROSject, we have three main packages: PanAndTilt Common, which are all the code that you need for the simulation, and that it will be shared with the simulation and with the real robot. Okay, and then we have these two dependencies that are person sim, that we use this to simulate persons, and then we have spawn robot tools, which is a package that we generated here in the construct that basically makes spawning, URDFs, SDFs, chakras, and other stuff much easier. Yeah. So here we have the simulation already. So let's have a look what we have here. So we have our person that we're going to use for the face tracking, and then we have a dummy head that we will do the paper of the pan and tilt. Yeah. Okay. So let's go to the notebook. So when you have this already launched, then let's have a look at the simulation which you'll need to create. Yeah. So I'm explaining all this for the pan and tilt, but more or less it's the same structure in any robot whatsoever. So if you go to pan and tilt control and you go to pan and tilt description, first of all, the name of the package, which is pan and tilt description. We here in the construct, we made like a standard way of doing packages for ourselves, and we highly recommend that you do so also. All the things that have to do with simulations, do it in pan and tilt, so then the name of the simulation and underscore description, because other people will understand what it is. If you put pan and tilt, I don't know what, no one will know what's that package for, okay? So essentially what we have done is launching this main sim. So let's have a look. It's a normal launch like always, and what we're doing is launching a gazebo world with this light world, which if we go here to the worlds and we have a look, it's very simple world, which is a ground plane and a spotlight. The spotlight, it's needed so that the camera can do face tracking. Otherwise, without lights, a bit difficult. Okay, so we have the world. Now we need to spawn. So we have these two launches, which are spawn the pan and tilt and control the pan and tilt. This one spawns the physical simulation, but doesn't activate the control, and this one will activate the control. Yeah? So we'll have a look, especially at this one, because I think it's more important and useful for people that want to do the transition from real robots to simulation. And yeah, and then we start the pan and tilt server that we will talk in depth. And finally, we initialize the person, which spawns the person. This is in person sim, so this is a Git that it's public, so you can have a look. I've left in the video, in the notebook, the Git, so you can have a look. And finally, we start this ICOG face tracker that we're using, and we start the tracker. So, what does this mean? So let's go step by step. So let's have a look at the simulation. We won't go much into detail, but I want to explain the structure. So essentially what we do when we spawn pan and tilt chakra, we're calling this launch. And as you can see, we're using the spawn robot tools package and spawn robot chakra multiple. That allows us basically to give a name and a chakra file and the position and orientation, and it will manage the spawning in gazebo. So I highly recommend that you use this to have less problems spawning stuff in gazebo. So let's have a look at this pan and tilt chakra. So this structure is used by loads of robots made in gazebo. It allows you to make simulations much more modular, and you can, like for example, I don't want to put the face, or I don't want to put the camera. I just go here and I just comment. Then if I spawn again, we won't have the camera. Yeah. So that's the main advantage of using chakras. And here we have defined different chakras that will be loaded and used by these that were defined in face or in main camera. So I want you to just have a look at the face basically. which would be, if you had to create your own, this would be the main structure that would generate the simulation. And essentially what we have is just a base link and a yaw and a pitch. Yeah, so that's the basic definition of a pan and tilt. And then we have this face link, which is the one that has this mesh head. It's this one that we are seeing here. Yeah, you would use the one that you want. And that's quite it. Remember always to put the gazebo parameters to have physical properties, yeah, and the materials. And yeah, that's more or less what I wanted to talk about the simulation. I know there's a lot of stuff, but we don't have time to go in depth there. So let's go back. So once we have the spawn and we have the control, let me just show you. It's a very, very basic control. We just have a state publisher, and then we have a position controller for pitch and yaw. So very simple. If you go here, and I'm explaining this just because it's important to understand afterwards for the phase tracking server. So there we go. So if you do a ROS topic echo, let's try it. We have these controllers, so position controller here, and then we have the other one right there, the yaw and the pitch, which it's here, exactly, yeah. And with these commands, you can move the header run. We're going to do it in a minute. So let's go to the notebook again. Let's move the pan and tilt manually, okay? And then I'll explain the pan and tilt server and so on, so you can have a more in-depth idea of what we're doing. So we open this shell and we launch. There we go. Let me put it here and let me open the simulation window here. There we go. Okay. So basically, this client, what it does is use the server that we just launched. We are going to see in a minute how it's done. And if, for example, I say, I don't know, like these and 0 tilt, and you see that the simulation just moved there. Or I can put like 0 and 45 degrees. There you go. So basically, it's how I control the servers, the simulated servers inside the simulation. It's very important to note that this will be exactly the same for the real robot. Yeah. So let's have a look how this works. So let's go to the main launch. And you see that we start this start pan and tilt server sim launch. So let's have a look. It's in pan and tilt control. Again, I highly recommend that things that are not related to the simulation, put them in a package elsewhere and that has an appropriate name for that. So let's have a look. So it's start pan and tilt server. And there we go. So you can see that it's just starting a Python script, and that has two arguments. The hardware, so if it's simulated or not, and if we're using Raspberry Pi. And you say, why do I need this? So let's have a look. So if we go to pan and tilt server and have a look there. There we go. So this is the heart, beating heart of this, because it allows us to essentially use afterwards the phase tracking without caring if it's a simulation or the real robot. And this is the power of ROS, that it allows us through topics to decouple simulation or real robot from anything else. That way you can generate code for both or for other systems, yeah, that use the same protocol of the same topics or the same services. Yeah, so I won't go into detail again, but essentially what it is a class that subscribes to this PanAndTilt topic, which has this custom PanAndTilt messages. So let's have a look. And there's no mystery here, so it's just two floats, pan and tilt, nothing very special. And for the people that don't know a lot of ROS, you'll have to change this in the CMake lists. So to configure this so that you have this compiled here, okay, in the CMake list. Yep. Okay, so essentially we have this that reads from this topic, and then we initialize a class depending on if it's simulated or not. Why? Because this server is the one that communicates these values to the simulation or to the real robot to move the servos. Yeah. So if we go to these two that are defined, so you can see that this one is defined in the moveSim, and this one is defined in the PanAndTilt move package, which is defined in the real one. So in this case, we don't have it here. Yeah. Okay. So, and in the simulation, if we go here in the tilt moveSim, what it does is publish in those commands that I showed you just a minute ago. Yeah. Okay. So let's have a look. There you go. So we have, and yeah. So now let me show you through the GUI graphical interface what we have to connect to the last one. So there you have the face tracking, that it's already doing the face tracking there. You see the square there. And this is being published in a topic called, I think it was faces. Face. There you go. So it's detecting the face. And that connects with the next part, which is the face tracking. Yeah. So let's go to the ID again. So this is clear, right? So we have the simulation that has the world. We spawn the PanAndTilt that it's simulated, that we talked about there. And then we start the server that takes in PanAndTilt commands so that someone tells it where to move the servos. Yeah? Who's that one? Well, now we don't have it activated, and that's because we will have to launch it, okay? So just talk about the tracker, which is the one that publishes the faces that we will use to then send the commands to the PanAndTilt, okay? So talk about this, I won't go into depth because it's a package of its own. I've left the Git so you can have a look. Essentially, what I want to talk about is this. This package that we just copied and made our own here, we modified it so that it takes these two, this topic, which is the name of your camera feed, yeah, of your camera topic. And from there, it just makes all the things that it has to do to give you the face topic that we just saw here for the detections. Yeah. Just a warning that I tell you here is the fact that you have to be very careful where this is taking the Hark Escape frontal XML, because by default it takes it from one place that maybe you won't have it. So to change it, just go to the source in the ICOG face tracker, and there you'll find, let me just look for it quick. Here we go. Okay, so here you will state the file, okay? Yeah, perfect. So that's quite it. So let's have a look on how to use all this data. So we have the PanAndTilt publisher, we have subscriber story, and we have the faces publisher. Yeah. So now we have to join these two things together. So we go here and we launch this start face tracker. Okay, so let me just, okay, so what happened there? Let me show you there. It's a very good exercise, that. So if we go to this start face tracker, which is in PanAndTilt control, let me close this face tracker. You see that I'm starting with these values, which are for the real one. So what do I have to do? Just comment. This, what it does is initialize my face, my PanAndTilt, in a position where I hope that I find some faces. Yeah, because I don't have searching faces mechanism implemented here. So there we go. So we go here again and start it again. Okay, there we go. So now it moved and we have face tracking. So you see that it's trying to track the face of the person. So now we can go here to the GUI and you see that it's tracking. Perfect. Now let's do it a bit more complicated for him. So let's move the person. Okay. Okay. So let me put this on this here. You can see. Here we go. So now with the keyboard, you can move the person around and do it again, and you see that it adapts and centers the face again to where it was. Let's move it once more. Too many windows here. Okay, there we go. There we go again. So there we have it. So it's tracking, and moving to the person. Great. So we have our system already running. I don't know how I'm going on time. So, yeah, so let me just, yeah, so I think I'm going to go to, yeah, let me show you this. So now we have the face tracking working in simulation, everything working, no problem. So now that we have it more or less working, now it's time to connect to the real robot. Yeah. So let's do that. So I can finish the simulation. Let's close everything. Okay, and now let's jump to the other notebook. So you won't have the PanAndTilt at home, I suppose, but you can do the same procedure as I'm doing here in your local computers and consider that local computer as the pan and tilt. You won't be able to move it, but you'll be able to do the connections and all that stuff, yeah? So, real connection. First thing is close the simulation because we don't want anything published there. And the first thing is that we need to install this real ROSDS real robot connection Git inside our robot. In this case, my PanAndTilt. So let me share. There we go. So I have it already here. So let me just go out. So, as I said, you won't be able to move a PanAndTilt, but you'll be able to connect to your system and install and all that stuff. Okay. So, there we go. So you would have to do an SSH to your system, and then clone this repo. And if you go here, you have this real robot setup, which we go to our, you just have to execute it like that. I won't do it because I've already installed it. Yeah, but basically that's it. So how can you get the IP of the robot? You can do it in many ways. You can use an application that scans all your system and gets the IP of your robot, or just connect and then do an if config. Well, in this case, you should know it, and somehow, once you have it, then you can get inside and do if config. Sorry. Okay, let's continue. So now, let's do the connection. So we have to connect ROSDS side. So you go to Real Robots and click here to activate it. Great. This is one side. The other side is you have to connect to the IP of your robot. In this case, that's mine, and 2 dots and 3000, which is a server that it's installed through that command, and it will be demonized and it will be running all the time. Yeah, so if we refresh, then we have to click here to turn on. And it will give us two things. One, the device name, which is the one that we stated here. So I'm going to copy this one, and I'm going to put it here. And then I'm going to also copy this. This is the URL that will be unique for my robot. Yeah, and connect. Fantastic. So now we are good to go. So in theory, now we are able to ping, to see ROS topics, and to launch things in the real robot. So let's see if that's true. So one of the first tests that we can do is, let me go here. Inside the PanAndTilt, in your case, you won't have the PanAndTilt. You'll have whatever robot you have or whatever computer you have. So we'll ping this name. It's always the same because in ROSDS, it has always the same name, the systems. Yeah. So let's ping. And there we have it. So there's a connection from the PanAndTilt or from your computer to ROSDS. Let's do it the other way around. So let's go here and do a PanAndTilt from ROSDS. So I'm going here, any web shell will do, and PanAndTilt. There we go. So 48 milliseconds, more or less. So great, fantastic. And let's test that ROS works. So the best way to do it is just to publish a simple topic. So let me put this one, for example, from, again, your PC, and from my side, the pen and tilt, double tab, and put ROScon Dev 2, pen and tilt. And let's put a rate of 1 second. Sorry, let me just, I don't know what happened there. Oh, yeah. Very good mistake from my side. Sorry for that. So what happened there? Oh my, oh my, oh my. So it's because we have to launch a ROS core. Where? It depends. So in my case, I've set it in pen and tilt. You can put it in ROS Development Studio as you wish. So now let's do that again. ROS core. Okay. And now topic. Okay. And now let's have a look what's here. ROS topic list. And we have it there, ROS topic echo and pen and tilt test. There we go. Fantastic. And to test the other way around, it's the other way around. So let's do it fast. Copy, paste this. Publishing, and now we do ROS topic list here. Topic.
How is
Echo. Right. And there we are. I am ROSDS. Fantastic. So we have set up everything. So in theory, we have ROS connected to ROSDS connected to our pen and tilt or to your computer. Okay, your local computer. I reiterate this because it's a concept that maybe it's a bit tricky at first. ROSDS is not your computer, it's server around there, and the other thing is your computer, okay? So now that we have that settled out, so let's have a look. What do we have to set up in my pen and tilt? Let's go here, and we need a Catkin workspace, and inside it we have copied two things. One, the pen and tilt control git, which we have talked about a lot, and the other one is the pen and tilt real robot, which is one that we didn't have. Why? Because we weren't in the real robot. And this one has only the things related to physical stuff, like the camera, how to set up, and different kind of systems and so on. I won't go into detail there, but we have video tutorials about this. So, and I think I left some indications in the notebook. And so, let's have a look now how to do everything. Yeah. So let's kill first the ROS core because we don't need it now. Now we go to the pen and tilt to your computer. In my case, the pen and tilt. Yeah. And now ROS launch pen and tilt real. This will start all the systems related to the real pen and tilt. So it will activate the camera, it will do all the stuff that we need. Yeah? Okay, great. So now, in ROSDS shell, what can we do? So we go to the shell, we do ROS topic list, And see here that now we have some other topics that we are not publishing anywhere. So that's because we're publishing through the real robot connection. So now we are going to, for example, let's launch the client that we launched previously. So there we go. Okay. Okay. And now for this, I might need to change my camera. Okay. There we go. Let me unshare the screen just a minute. And oh, sorry. There we go. Okay. So here, let me share my screen. It's okay there in control?
Everything okay.
Okay. So now I'm going to go to ROSDS. There we go. And let me, for example, put 90 degrees and 0. There we go. And let me put it a bit better so you can see better. And let's do, for example, 90 degrees and 40 degrees also. There we go. So I want to make this clear that we are communicating through ROSDS to the real robot through this real robot connection. Okay. And finally, let's have a look at the cameras. So okay, let me select the camera that we are inside. Yeah. Okay, so you're seeing my feed of the camera here. Okay, yeah, sorry. So I have to share my screen for that. Okay, share. There we go. Sorry about that. Okay. So now you see the feed. There we are. And finally, we're going to start the face tracking. So we have this reel that we just started here. And now we're going to launch the face tracker in ROSDS. Okay. So I can cancel this. Face tracker. Remember that we have to go here and change this to real values, because this ones are the ones that I saw that they work. Okay, and we launch it. Okay, so there we go. Okay, so let me show you because it's quite cumbersome this. So I'm going to. It's okay. Okay, so let me stop sharing and put my camera. So there we go. So now it's moving. I'm moving my head and it's tracking me more or less. There we go. There we go. As you can see, we can do it much better, but it's not from the connection, it's just my algorithm for tracking. It's a bit dodgy. But there you have it. So it's tracking me, but the face tracking is being executed in ROSDS remotely. Yeah? And thanks to the work that we did with the simulation, I could do this really fast. So I could change from the simulation to the real one in a matter of 1 day, instead of reiterating and doing these tests to make it work in the real robot, which would be very slow. And yeah, I think I'm finished. Let me share my...
Hey, so thank you very much, Miguel. Thank you. Thank you a lot. Thank you a lot.
Okay. There we go.
Okay, let's see if we can see your face. Yes, that's correct. And now let's go and get the questions from the chat. So people in the chat, please start asking your questions. And let me start myself
with one of them.
Just a second, let me remove this double the sound that we have here. Second. Okay. Okay, here we are. So the first question from my side is, can the face recognition be faster? Because we have seen that it was very slow. So why does it go slow?
So as I said, it goes slow not because the face tracking is the face detection, let's say, is not working. So it's working really well. And as you saw when I echoed, the face tracking in simulation was like super fast. It goes slow just because my algorithm that takes the faces topic data and gets it, processes it, and sends it to the servos or to the simulation is not well optimized. So I think we could do it much faster, for sure.
Okay. Now we have here one question from Merlin that I don't know if I understand correctly, but he says that is there some part of the message forwarding infrastructure that is available as open source? And he means to connect, for example, two ROS setups in different remote local networks.
Okay, you mean, okay, so connect two local networks between them, and yeah. So if there's infrastructure, yeah. There are some infrastructures that are more cumbersome to set up than others, but you can do them like the basic ROS way, which would be to set up the ROS IP and so on, and the ROS host name, and you could connect them with a lot of work, but it could be done, yeah. You can use also our system to connect, at least in the future, we will be able to connect like several, so you could connect all of them and connect them through ROSDS. And also you can do your own protocol to do this, which also work, but it can be done. But if you're interested, we'll leave some links to all that documentation so that you can do it. Yeah.
Okay, yeah. So I think that he also afterwards he explained something.
Okay.
Here, and I meant what is used to connect PanAndTilt to ROSDS in the presentation, and I think that he means about the usernet, for example.
Yeah. So we are using the usernet from Husarion, yeah. And what we're doing is setting up there in ROSDS some systems so that it's easy to do it. So for that, you just have to do what I told, just download that Git and then execute that command that it's robot setup, blah, blah, blah. And that will set up a daemon that allows you to do these connections. So it's really simple, as you can see.
Okay, makes perfect sense. And now another question from Laria Michael. He says it's very interesting. He says, is the processing too much for the Raspberry Pi?
Very good question. So, this was one question that so the thing is, Raspberry Pi can't do this. So it's a lot of processing. But it can do the face, at least it can do it. So I've seen that it can go more or less okay. It's bad for the Raspberry Pi, it's things like deep learning. That's impossible for him. And that's one of the things that it's really useful to decouple and execute like the local hardware stuff inside PanAndTilt, and then just publish, for example, the images, okay? And then in a remote server or ROSDS or whatever, you have the processing power to do deep learning, for example. So answering the question, for the face, it's okay, it goes okay. For anything else, it's too much.
More questions here for you. From FreeMind, he says, in the simulation, why was the robot moving a little bit when the human object was completely stationary?
Yeah, very good question, very good eye. So that's the thing that I did this algorithm to track. It's not the best way because it just gets the image of the camera, and then it gets the face's detection. And what it does is try to put it in the center. So you have like a square of the person, like this, and it's the center like that. So I have like a displacement, and what I do is just say, okay, so it's displaced to the left, so I move to the right, just one step, and then I recalculate. It can be done much better. And why it moves, it's because it goes, and when it gets to a place, then it goes past it and then goes back again. It's that. So it's just to make the algorithm better, and it wouldn't do that for sure.
Okay, another, let's say the final question, okay, because we are already getting late, and let's go by my biomed school question that says, if I construct an algorithm in simulation and generate a model file and finally coding it to the real world, will work with minimal modifications. And I think that he meant about, for example, the problem with transferring models generated in the simulation and transferring those models into the real world, like the thing that you did for the domain randomization of fetch, for example.
Okay, see, if it's that, so I suppose it means AI deep learning models that you generate in the AI. So the answer is, if the simulation is good enough and the AI algorithm is good enough, the transition shouldn't be, it should be seamless. Because, for example, we did these experiments for domain randomization, which what we did was, in the simulation, we changed all the parameters of, let's say, the physics. So the colors, the lights, the shapes, and so on. And that trained the system so that the models that generated afterwards in the real world would apply much better. Yeah. So it depends on how you did the training and if the simulation was like hard enough, so it contemplated all the facts and all the cases.
Okay, Miguel, thank you very much again. Miguel, thank you very much again for the presentation. And let's continue then.
Yeah, so let's go with the last presentation. Please
today.
tell us some, today the last one already.
Yeah.
Please tell us some detail. What we're going to learn in this last presentation.
Yes, on the previous one, we have learned a very interesting skill for robot that was face tracking. Another one very interesting is to find where an object is. So it is that the robot has to look for a specific object in an environment. So that's what we are going to see today, how to search, how the robot can search for one specific object in an unknown environment. So provided that the robot doesn't have a map of the system.
Okay,
please.
So let's welcome the last keynote speakers, the city of Husarion, Dominik Nowak, and his colleague Lucas Mitaka from Husarion also. Welcome.
Welcome.
Okay. So simulation of the robot, change simulation. Let's restart tutorial 9. Oh yeah, it's starting, very good. So once more I will open graphical tools to tell you a little bit more about what is happening in the system. Let's open also RQT graph to visualize the system. Okay, so let's go. As you can see, RQT graph is quite complex. So we use out-of-the-box ready working ROS nodes here instead of this single one called Search Manager. So Search Manager is responsible for let's say performing the whole search task. Its code is quite complex. I will open it in the next few minutes and tell a little bit more about that. And yeah, we are getting data from LiDAR. Explore server is creating a map of the environment. It is and then Search Manager is controlling the movement of the robot based on the signals from RGBD camera and LiDAR. Oh yes, and ROSbot once more has finished its tasks. So that's the image from the RGBD camera, what you can see right now. So robot found stop sign. And yeah, so basically robot checked all obstacles, all objects that are present on that map. And as soon as it finds the target object, it stops. Let's open IDE to show you the key nodes that we developed to perform Search Manager tasks. So Catkin workspace, source, and Search Manager node CPP. So here's the whole source code of the node that we created. So it contains more than 500 lines of code. So I will not go much into details of how it works, but the source code is open and it is explained in details in our tutorial number 9. And yeah, we have also created a few launch files showing you how to so dedicated for a physical robot, for a simulation environment, because you need to change them a little bit to adjust them to a specific environment. I think we'll done in let's say describing you in high level how the system works.
So now let me tell a little bit about second half of our tutorial. I will demonstrate you, together with you, Łukasz, how to connect that simulation environment with the physical robot. We will need to have a physical robot, of course, and this physical robot is present in my home right now. Łukasz is present somewhere else, and Łukasz will connect to that robot from the level of his own ROS development studio environment, and show you how to open run the same tasks as I did before in the simulation environment. Let me show you how to do that from the level of ROS Development Studio. In the ROS Development Studio, you will find a button Real Robot. So let's connect that, and you can see connect ROSDS to a Real Robot, and provided by Husarion. So let me tell a little bit more about how connection between simulation environment and development environment and physical robot is done. So basically, that simulation environment and robot will be in the same VPN network. Problem with classical VPN network is that latency is many times too high. And they do not work well with ROS. It's quite complex to make working typical VPN solutions with ROS. And with high latency, it's also much harder to do. The connection is provided by Husarion. Husarion is a peer-to-peer VPN network, so the latency between simulation environment and robot is as low as possible. So that's direct peer-to-peer link, so you don't need to worry about too high latency. Right now, Łukasz will share his own ROSDS environment with you. But at first, we need to open a server working on a physical robot that allows you to connect to the simulation environment. So IP address of the robot is in my Wi-Fi network is as follows: is 192.168.0.87, right? And on port 3000 there is that website, and on that website you can configure the robot name and generate a link. So robot is right now probably connected to the environment of Łukasz. So Łukasz, can you share your desktop right now with us?
And share my desktop. I think you should see it now.
Yeah, we can hear. We can see you. Yeah, Lucas.
And I can start working with my desktop. It's already connected. Yeah. We can see that I'm already connected with ROSbot. It's connecting to connect with. I'm providing the default by start the launch file, which is supporting the leader, the camera, and all the device, the controllers in the ROSbot. this is the launch file which is dedicated for ROSbot part. Now I'm opening the additional terminal. In this one I will start the launch file required for opening AirViews and graphical tools for the RDS side. At this moment, the ROSbot is already working. The leader should be taking the scans and camera taking the pictures. On the terminal, you can see that the map is being updated. Now we'll start the search manager, which will manage the setting the goals for ROSbot. Okay, it's starting, so now we can switch for graphical tools.
So guys, I just changed.
Okay, we are seeing the RVs and environment where the ROSbot is located. You can see that there are scans from the leader, and now we've got the map appeared. So in the moment ROSbot should start searching. Yeah, we can see how it moves. And in a moment it should, I think it will find the object.
Yeah, and I'm streaming the image showing how robot is performing its tasks right now. Yes, so Łukasz, maybe tell a little bit more about this color in the RVs.
Okay, you can observe how as the ROSbot is traversing through the environment, the pink areas which are being marked are the obstacles that have been already checked by ROSbot, and they're marked as there is no search object. And as the ROSbot is moving further, it will search all the obstacles to check if there is the object we are searching for.
Oh yeah, he did.
Okay, and so we can see now that the objects have been marked, so the ROSbot have found the search object is the stop sign, and that's the finished task.
Yes.
So I think we can switch back to the Dominik.
Yeah.
Okay, thank you, Luca. Thanks a lot. Great.
Yeah, and the whole time I was streaming the image how the robot is performing in the physical environment. I'm not sure whether you have seen it.
Yeah, we have seen it. We've been streaming Lucas and your image, both.
Okay, perfect. So as you can see, we can run that simulation, that code both in the simulation environment and on the physical robot in a very similar way. And that's very good because we can iterate really fast in the simulation environment with our source code, and then one-to-one we can move the same code to the physical robot and see that the algorithm is performing the same way in simulation and in real environment, and it's great to see that. So the project, the source code was very complex to analyze that line by line. But all attendees has got access to the detailed tutorial describing all important, let's say, file and function. But as you can see, the robot is performing well. It did its tasks, but of course you can add new functionalities to that tutorial. That the robot, for example, could have a web UI in which you can send photos of objects you'd like to let them find. So it would be a very nice robot solving real life problems, because all of us sometimes has lost something, so such
devices could be really useful. Okay, great, thanks, Dominik. So can you share your screen so we can see you?
Yes, sure.
Yeah.
Okay, so now it's time to go to the question section. Thank you, Dominik, and thank you, Lucas. Let's go for the questions, guys. That you are there, go and post your questions on the chat. And in the meantime, that people is preparing their questions. Let me ask you the first one myself. So you have shown how to recognize the stop signal. But what will happen with the performance of the object recognition system when you try to recognize more than one object, say 10 million objects? Do we remember any increase in the performance?
Ricardo, you whether we can recognize multiple objects, right? Ricardo, can you hear us?
No. Yeah. Go ahead.
Okay, so yeah, that system can recognize not only one object but as many objects as you want. To perform object recognition, we use find object 3D ROS component. So basically, we can teach that ROS component to recognize as many objects as we want. As soon as any of the objects in the folder of let's say of learned object is found, robot stops, allowing you to go to that object and take it. And then you can go to finding the next objects.
Okay. So let me ask you one of the questions from the audience. Can you please share some more details about the algorithms used in this presentation? And this is a question from Ludovic, and he also asked for any scientific paper, but I don't know if you are remembering that now. But if you can share some details about the algorithm used for the object recognition. Well, actually, he doesn't specify if it is the object recognition or the decision making for going into one direction or another.
Okay, if it's about going for the selected points, the search algorithm is divided to two stages. First stage is discovering all accessible points. It's based on a frontier exploration algorithm, and second part is checking each object with the camera, and we're selecting basically the closest point, which is the closest point to robot, which was still not inspected.
Okay, and then related to that, there is a question from Osaid Sahib that says, are you using some path planning algorithm in order to decide where to go searching for the object?
So we're setting the object as I thought is the closest object we want to find, but we're setting on the position. It's the place from which we want to observe the object, and for moving to the specified object is move base. It's a ROS component.
Yeah, the typical ROS navigation stack.
Yeah, that's right.
Okay, great. Then another question here from Benu Samprati. He says, is the robot exploring a new environment, performing a slam while searching for the object?
Yes, it is. It's searching with the environment which is unknown before.
Okay, and he would like to know also about the sensors that you are using for the whole demo that you have done. So which sensor are you using for recognizing the object, for finding where it is?
Okay, so we're using the laser scanner is RP LiDAR A2, and camera is Arbacastra.
Okay, so yeah, Benu was asking also for the details, but I think that you have mentioned the brand itself. So Benu, you can just go and buy the camera or check for the data sheet on internet for those have mentioned by Luca. Okay, so I think that is all for your presentation. Thanks a lot, Dominik and Luca, for your amazing presentation. Thank you.
Thank you, Ricardo, and thank you all attendees.
Thank you, Luca and Dominik, bring us this super presentation and showing a real robot moving and searching. What are you doing?
I was trying to apply what Lucas and Dominik they have shown me, because I wanted to find if my robot can figure out where are my pair of socks that I have lost, and I don't know, because it's a search object program.
Nice. Okay.
Okay, we'll continue later.
We'll continue to see it.
Okay.
So today, I think, excellent presentation. Yeah.
Yes, amazing talks, amazing presentations, and amazing information that all of you have on your ROSject. Remember that you can go back and check all the code and reproduce the results yourselves.
And do we have a last lottery for this session?
Yeah, I think that we can do a last lottery, very quick, fast lottery now. So if you can put me the screen of the lottery in there. So we are stressing Miguel now for moving the back. Okay, here, there it is. Remember, the winner will take the last t-shirt of today. I am a ROS developer. Okay, I would like to have one also. So then what is the question? Let's go for the final question. Okay, so go to the chat and then say which one is the type of features for object recognition that were used on by this object recognition software. And here we have the winner. Biomed School says surf and or yes, so one of those is. So we have the winner who is Biomed School. So Biomed School, you got the t-shirt for today.
Well done.
Yeah, the final one. Very good. Don't worry, tomorrow we'll have more. Okay, so now let's go to the closing of the conference for today. And let me do a small recap of what we have learned today. First, we have learned how to find an object in an unknown environment. That has been by Dominik and Luca's last talk. Then also previously we have been learning how to control PanAndTilt in order to follow a phase, to track a phase. Then also previously we learned how to transfer one ROS1 Python node into a ROS2 node. And previously, on the previous one, we learned with Luca about how to segment the objects that are on top of a table.
Yeah.
It was a lot of material, a lot.
Amazing lesson.
Yeah.
And thank you for joining us, everyone. Remember, tomorrow we also have 4 practical presentations. We will have Tomoya from Sony, Carlos from Beta Robot, and James from Clemson University. We also have Davide from Blue Ocean Robotics. And tomorrow we will start at 7:30 a.m. in CEST time. So remember to come have a very good breakfast, okay?
And coffee, of course.
Yeah, for sure. Okay. And we are going to publish the video recording of the whole conference in our channel. So stay tuned.
Yep, now before we go, just a little bit thing is that let me share with you the link with that on the chat. It's a link for a conference poll. It's actually is an assessment that it will take you only 1 minute. And if you can make us the favor to fill it and also then answer what is your opinion about the conference, then you can help us to skyrocket our conference. Okay, we want to improve, we want to do it better, bigger and leaner and with more fun, of course, always. Okay, so I think that this is all. Do we have the question on the chat already? Yes, so you have the question there, on the chat. If you click on that link, then you will get the form with all the questions. It's very simple. It's just click, 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 and that's all.
Yeah.
And that's all for today, isn't it?
Yes, we're done. But wait. I just received a live feedback from a fan in America. Let's connect with him.
Okay. As a fan from the USA, then we have to connect. Yeah, of course. Let's go to him and see what is his feedback about the conference. Oh, he approves. Yes, that's great.
Thank you. See you tomorrow.
Yeah, see you tomorrow, guys, with more ROS. Bye.
Keep ROSing.